Welcome to AI Paper Podcasts. Today we're diving into a really interesting paper, Challenges and Paths Towards AI for Software Engineering. It's got authors from MIT, CSAIL, Berkeley, Cornell, Stanford, UPenn, quite the lineup.
Yeah, a strong group.
And for everyone tuning in, especially if you're deep in AI research or ML engineering, the key takeaway up front is this. AI's role in software is getting way broader than just, writing code snippets.
Absolutely.
This paper does a great job laying out the current state, highlighting the big challenges, and pointing towards what might be next. It feels like a really solid overview for staying current.
It really is. What I like is how structured it is. It's not just a random list of AI tricks. It's a framework for thinking about AI across the whole software engineering lifecycle where it works, and importantly, where it still struggles.
Okay, so let's get into that structure. Their taxonomy for AI tasks in software engineering, how do they break it down beyond just AI writes code?
Well, they use three main measures, which I think is quite useful. First is scope. Think like how big is the change?
Scope, okay.
Yeah, is it just one function? That's the small end.
Mm-hmm.
Benchmarks like human eval, MBPP, they test that.
Right.
Then there's what they call a self-contained unit, maybe a whole file, a class, bigger impact. Think full stack bench, big code bench.
Makes sense.
And the largest scope is project level, changes across the entire repo. Commit 0, SW bench, those are trying to measure that kind of capability.
That distinction feels critical. Modifying one function versus refactoring a whole project are totally different beasts. What are the other two measures?
Second is logical complexity. Pretty much what it sounds like, how much intricate reasoning or complex transformation is needed, low to high.
Okay.
And the third is the level of human intervention. How much does a person need to be involved? From none, full autonomy, the dream, right? All the way to needing significant human guidance.
Got it. Scope, complexity, human intervention. So using these, what specific software engineering tasks do they map out?
They cover a lot of ground. Code generation, naturally, is front and center.
Usual suspect.
Yeah, includes things like code completion, the tab completion we all use, GitHub Copilot being a prime example, but also the more ambitious stuff like generating code directly from natural language descriptions.
Right, the headline grabber recently. Yeah. But they go further into code transformation. That sounds really important.
It absolutely is. And it breaks down into a few key areas. First, code refactoring.
Mm-hmm.
This is where you take code that works, but you rewrite it to make it better, more maintainable, easier to read, maybe more extensible, but crucially, without changing what it does.
Keeping the behavior the same.
Exactly. Right. They mentioned the rule of 3, sort of a guideline that maybe you refactor after you see the same code pattern 3 times.
Oh, yeah.
And a huge example of this in the real world was the React Fiber rewrite. That was a massive refactoring effort driven by performance and maintainability needs. It really shows you need more than just correctness. You need a sense of code quality.
So it's about future-proofing the code, making it something humans can actually work with long-term. What else is under transformation?
Next is code migration and translation. This is often a massive undertaking. Think about moving a huge old code base to a new language or platform.
Oh boy.
Yeah, it's high scope, high logical complexity, almost always. Migrating from, say, Scala 2.13 to Scala 3, you've got changes in macros, type systems, library incompatibilities. It's tough.
I can imagine.
Or think about moving off COBOL. Still runs critical systems, but finding COBOL programmers, increasingly hard. Migrating that to something like Java is a monumental task.
Huge scope.
Definitely. And you see companies doing this for good reasons. Twitter moving to Java Scala for lower latency is a good example. And the whole push to translate C code to Rust for memory safety that's super complex. DARPA's involved. You have tools like Syzygy, C2 Safe for Rust. Trying to get correctness, speed, and idiomatic Rust code is a massive challenge.
It really sounds like untangling a giant evolving knot of logic.
That's a good way to put it. Then, the last part of code transformation they cover is code optimization. Improving performance speed, memory, while again, keeping correctness.
The balancing act.
Exactly. And the search space for potential optimizations is often enormous, with competing goals like making it faster might make it harder to read or use more memory.
Right.
Google Chrome's performance work over the years is a great case study. Constant tweaking of the V8 engine, adding things like concurrent garbage collection, turbofan. It requires deep, sustained effort.
Okay, so generation, transformation. What other big buckets of software engineering work are they looking at through this AI lens?
They move on to software testing and program analysis. Testing covers all the ways we try to find bugs. Unit tests, property-based testing. Fuzzing, mutation testing, where you deliberately break the code slightly to see if tests fail like they should. The goal is just reliably finding bugs.
A never-ending battle.
Tell me about it. Scalability and the effort of writing good tests are big challenges, and this is an area where LLMs are starting to show promise, like automatically generating test cases.
Interesting. And program analysis.
That's about getting assurances about correctness without necessarily finding specific bugs through testing. Static analysis tools like linters that check your code style or potential issues without running it.
Okay.
And dynamic analysis, like using debuggers while the code is running. And then sort of the ultimate goal in this area is program repair AI automatically fixing the bugs it finds.
The dream. Fix my bugs for me.
Wouldn't that be nice?
Okay.
Then there's software maintenance, which, let's be honest, is where most software projects spend most of their time and money.
So true.
This includes code documentation and summarization. LLMs are actually getting pretty decent at generating doc strings or summaries.
Yeah, I've seen some of that.
Also, pull requests, PR review, automating some of the checks for style, simple bugs, making sure tests pass. They see this as generally lower logical complexity.
Okay.
And finally, code understanding, navigation, and question answering. Basically helping developers figure out large, unfamiliar code bases. Super important for productivity.
All those things that can chew up so much developer time.
Exactly. Then they have a category for scaffolding and metacode. Scaffolding is the support infrastructure authentication, setting up APIs, databases.
Plumbing.
Pretty much. And metacode is the code about the code test harnesses, build scripts, config files, CI/CD pipelines, Docker files, make files, all that stuff that makes the system work but isn't the core logic.
Right, the essential but maybe less glamorous parts.
Often small scope, low logical complexity, but needs a lot of very specific domain knowledge. They give an example of configuration validation using a tool called Siri, and how LLMs struggle with subtle things like dependencies or version constraints, sometimes just guessing based on popular parameters.
The subtle details matter.
They really do. Same with infrastructure as code, like Terraform. Getting security configurations right, understanding permission levels. The Terrateam ECS example they cite showed an LLM messing that up. Needs real semantic understanding.
Okay, that makes sense. One more category.
The last one is formal verification. This is the heavy stuff generating actual mathematical proofs that the code is correct. They distinguish between full functional verification, FFV, proving the entire spec, which is incredibly hard, mostly because writing the spec itself is hard.
Right.
And property verification, PV, proving specific critical properties like this function will never divide by 0. PV often struggles with false positives, though.
Where would you even use this?
Think safety critical systems. They mention the Ariane 5 rocket failure, the Therac 25 radiation accidents, cases where software errors had catastrophic consequences. Formal methods could potentially prevent those.
High stakes.
Very high. ComCert, a verified C compiler, is a famous success story here. But these tools aren't mainstream. Tools like Hoverty exist for PV, but they can be noisy, lots of false positives, high churn. It's tough. The hope is maybe LLMs could make writing the specifications or dealing with the tools easier someday.
It's fascinating seeing the whole software lifecycle broken down like this and thinking where AI fits, or might fit. But the paper isn't just a catalog, right? They hammer home the challenges.
Oh yeah, they dedicate a lot of space to the roadblocks. 9 key challenges they identify. First up, evaluation and benchmarks. This is a big one.
Oh, so?
They argue our current benchmarks are way too focused on just code generation, simple function completion.
Okay.
Plus, there's the worry about data contamination. Did the model already see the test questions during training? And fundamentally, do these scores actually predict if an AI will be useful for a real software engineer doing complex tasks? Often, the answer seems to be not really.
The benchmarks aren't capturing reality well enough.
Pretty much. There's a lack of diversity in what we even try to measure. Code QA, finding vulnerabilities, formal verification tasks, very few good benchmarks. And it's hard to measure things like, is the code clean? Is it idiomatic? Does the AI handle a back and forth conversation well? They question the construct validity. High scores don't always mean better developer experience.
So our measuring sticks might be misleading us. Right. What's challenge number 2?
Effective tool usage. This is huge. Real software engineers use tons of tools. Linters, debuggers, profilers, build systems, version control, IDEs, terminals.
Whole ecosystem.
Exactly. But current AI coding assistants, they They mostly just generate text. They don't know how to use these other tools effectively, how to run the linter, interpret the debugger output, execute commands.
Right.
We're seeing some baby steps like LLMs using calculators or web search, but integrating deeply with complex SWE tools is way harder. They mentioned this idea of an agent-computer interface to manage this.
Yeah, that gap seems critical.
Yeah.
Development isn't just typing code into a void. What about that human side?
Human-AI collaboration, still really clunky. We give vague instructions, the AI generates something plausible but wrong, we try again. It's frustrating.
The prompt engineering dance.
Totally. And there's limited controllability. You can't easily steer the generation process precisely. Interfaces are mostly just text prompts. There's this big abstraction gap between fuzzy natural language and precise code, especially for bigger programs. Plus, sometimes you need more than text, like sketching a UI or defining constraints for embedded systems. And software development is full of trade-offs: speed versus memory, readability versus conciseness. LLMs don't really get those nuances from a simple prompt.
Yeah, they just go for whatever statistically likely code comes next.
Kind of. They cite an astropy issue where an LLM wrote a data serializer but completely forgot the deserializer part. The implicit need wasn't understood. And unlike a human colleague, AI rarely says, that's ambiguous, could you clarify? It just guesses, often wrongly. Incorporating our implicit knowledge while keeping us in the loop is tough.
We need AI that's more of a collaborator, less of a slightly confused code generator.
Exactly, which leads into the next challenge: long horizon code planning. LLMs are generally bad at designing good, lasting abstractions.
Ah, the architecture stuff.
Yeah. Thinking ahead, choosing data structures, designing APIs, ensuring modularity, writing code that's easy to change later, that takes domain knowledge, experience, wisdom almost. LLMs are mostly optimized for local correctness right now.
So they might solve the immediate problem, but create a mess for the future.
They often do. They tend to produce more complex code than needed, or repeat code instead of creating a reusable function or class. They don't naturally think about maintainability or leveraging existing libraries effectively. It's a short-term focus.
Okay, that's a big one.
What's next? Large scope and long contexts. Real code bases are huge, millions of lines sometimes. Current methods like retrieval augmented generation, RAG, where you try to find relevant snippets to feed the LLM, they have limits.
RA isn't a silver bullet.
Apparently not for code, or not yet. Models retrieve the wrong stuff, or stuff that's syntactically similar but semantically different. They struggle to piece together information from multiple retrieved snippets or understand how to reuse code properly. The paper mentions a chart.js example where a standard retrieval method just failed to find the relevant files in the repo.
So finding the right context is hard.
And even when they get the right context, studies show they often misuse it, suggesting they don't truly understand its meaning or how it fits into the larger picture. Tasks like refactoring or debugging get way harder at the repo level.
It's like needing a map of the whole city, not just the street you're on.
Excellent analogy. Which ties into the next challenge: semantic understanding of code bases. A truly global understanding. What's the overall structure? Where is certain functionality implemented? How do the algorithms really work? What are the key invariants? LLMs struggle with this holistic view.
They know the words, but not the story.
Something like that. They're trained heavily on generation, maybe seeing lots of small, isolated examples. That doesn't necessarily teach them how to analyze a large, complex existing system with intricate logic. And knowledge doesn't always transfer well between different types of coding tasks either.
Okay, so understanding the big picture is hard.
Yeah.
What else?
Low resource languages and specialized libraries. This is a practical headache. Models train mostly on Python, Java, JavaScript. They often fall down hard when you ask them to work with less common languages or niche libraries they haven't seen much of.
They just haven't seen enough examples.
Right. You get syntax errors, basic misunderstandings of how the language works, or they just hallucinate library functions that don't exist. They mention models making up syntax in languages like Triton, or even inventing theorems in proof assistants like Lean.
Like trying to speak a language you only know a few phrases in.
Yeah.
Very badly.
Exactly. Then there's library and API version updates. Software is constantly changing. Libraries get updated. APIs change. New language features appear.
The ground is always shifting.
And LLMs trained on snapshots of code from the past struggle to keep up. They might use deprecated functions, ignore new, better ways of doing things, or mix syntax from different versions. Benchmarks like Code Update Arena are trying to test this, but it's a massive real-world problem across entire repositories.
How do they even begin to track that?
It's really hard. Adapting to new styles, patterns, paradigms like the introduction of React hooks or Python moving type hints from the typing module to built-ins, the models are slow to catch on. They might miss important security features added in updates. The incompatibility between Lean 3 and Lean 4 is another stark example. Staying current is a huge challenge.
Definitely feels like a major hurdle for practical use.
Any more challenges?
Last one they list is high logical complexity and out-of-distribution OD domains. Basically, tasks that are really hard even for expert humans.
Like inventing novel algorithms.
Or working in highly specialized domains with unique rules the model hasn't seen. Think formal verification of file systems using custom logics like crash war logic. These tasks are rare in training data. Models often rely on trying things and getting feedback, but for these cutting-edge problems, good feedback mechanisms might not even exist yet. Symbolic methods also have limits here, huge search spaces, weak verifiers. Without relevant data or good feedback, it's hard for models to get traction on these really tough, novel problems. Wow, okay, that's quite a list of challenges. It really puts the hype into perspective. We've come far, but there's a long road ahead for AI to be a truly capable software engineering partner.
Absolutely. It underscores the complexity of software engineering itself.
But the paper doesn't just leave us there, right? They do talk about paths forward.
Thankfully, yes. They spend a good chunk of the paper outlining promising research directions to tackle these challenges. They group them into data collection, training, and inference time approaches.
Okay, let's start with data collection. What needs to change there?
Two main thrusts. First, automatic data curation. The idea is to go beyond just raw source code in training data. We need to enrich it with more information about the code.
Like what kind of information?
Things you can get from static analysis, abstract syntax trees, ASTs, control flow graphs, CFGs, type information, data flow, or from dynamic analysis execution traces, memory usage, code coverage during tests, program states, even info from formal verification, like invariance.
So embedding deeper knowledge into the training data itself.
Exactly. And they also talk about generating high-quality synthetic data, especially for tasks where real data is scarce, or in constrained environments like domain-specific languages, DSLs, where you know the rules and can generate correct examples with specific properties. Think math problems, or maybe generating verified code snippets.
Moving beyond just scraping GitHub towards more structured, informative data. What about the human side of data?
That's the second part, human-centric data curation. We need finer-grained data about how developers actually work. Not just the final code, but the edits, the build successes and failures, the discussions and code reviews, maybe telemetry from IDEs, though obviously with huge privacy and IP caveats.
Capturing the process, not just the product.
Right. And we need data for more diverse tasks, like refactoring. That might mean finding paired repositories showing before and after states with good descriptions. And data that reflects real usage, vague requirements, back and forth clarification, maybe even non-text interactions like UI sketches. Platforms like Copilot Arena are starting to collect some of this interaction data.
So, richer data, more realistic data, more diverse data. Makes sense. What about training the models differently?
Several interesting ideas here. One is environment design for code RL, reinforcement learning. If we want AI agents to learn by doing, they need good environments to do in.
Like sandboxes?
Sort of, but more realistic. Making large, real-world code bases easily executable for an RL agent is a challenge. Think about automatically handling dependencies, setting up build environments, maybe using Docker. DeepMind's alpha code and efforts like SWE RL are steps in this direction.
And the reward signals for RL, just does it pass tests?
That's tricky too. Longer tasks have sparse rewards. There's a risk of reward hacking where the agent cheats and test coverage might be poor. So they suggest exploring rewards without execution, maybe using proxy metrics, or even training other LLMs to judge code quality based on semantics or structure.
Moving beyond simple pass-fail. What else on training?
Adapting to specialized and quickly changing code bases. How do you make a giant model work well on my specific, maybe obscure internal code base, or keep up with that library that updates every month?
Yeah, the currency problem again.
Exactly. They mention techniques like test time training, TTT, quick adaptation at inference time. Also, data strategies like generating synthetic code specific to that context, or learning from trajectories of past attempts within that code base, and maybe more efficient methods like prompt tuning or prefix tuning instead of full fine-tuning just to learn a new API style. The ultimate goal is models that can learn on the fly from a few examples, like in the Dreamcoder project.
Making models more adaptable and context-aware. Crucial.
Absolutely. And the last training point is training code LLMs to collaborate with humans better. This means teaching them to use specifications beyond just natural language, maybe formal specs or using tests as specs.
Right, making the communication clearer.
And crucially, teaching them to quantify uncertainty and communicate proactively, knowing when they're confident and when they're not. Asking for clarification instead of just hallucinating. Acknowledging limitations, maybe even training them on data that includes reasoning steps or explanations. The SWE agent example, where analyzing GitHub discussions helps solve issues, points towards this more interactive, communicative direction.
Building AI that's not just a generator, but a partner you can actually talk to. Okay, so better data, smarter training. What about at inference time, when the model is actually being used?
Several key ideas here too. First, semantic-aware embeddings and retrieval, moving beyond keyword matching or basic syntax similarity when finding relevant code context, the RAG part.
Making retrieval smarter.
Yeah, training embeddings that understand code's meaning and execution behavior. Maybe training the retriever itself to find the most helpful examples for the task at hand. Or even having the AI navigate the code base dynamically, using IDE-like functions or static analysis to find context.
More intelligent searching. What else?
Integration with SWE development frameworks. This is about making AI useful in the real world. It needs to understand more than just code editing. Think automated reviews that check for anti-patterns, assessing deployment risks, generating release notes, understanding CI/CD processes.
Embedding AI into the whole workflow.
Precisely. And learning to avoid common mistakes, maybe by collecting failure cases and using them as negative signals during training or RL.
Learning from its errors, hopefully.
Hopefully. Then, closely related, is incorporating SWE tools. Having the AI actively use linters, type checkers, profilers, debuggers, maybe through RL, learning when to run which tool, or neurosymbolic approaches that combine LLMs with formal methods.
The AI using the same tools a human would.
Exactly.
Yeah.
Using static analysis on generated code, feeding program structure info to the LLM, maybe using AI to help focus traditional PL tools, or even using deductive synthesis with rewrite rules in DSLs like Spiral or Halide to generate code that's correct by construction. LLMs helping compile for specialized hardware is another example.
So a tighter loop between the AI and the existing powerful tools. And the final point.
Scaffolding human supervision. Ensuring humans stay in control and can trust the AI. This means things like making the AI cite its sources or explain its reasoning, using interactive approaches like live programming, and just making the AI-generated code much more readable and interpretable. Trust and control are paramount.
It feels like the overarching theme here is integration. Integrating deeper knowledge into data. Integrating AI with tools and workflows, and integrating it more seamlessly with human developers. Not AI taking over, but AI becoming a much, much better assistant.
That sums it up perfectly. This paper really paints a picture of AI moving beyond just a fancy code generator towards being a truly capable software engineering assistant. The challenges are huge, no doubt, but these paths forward offer a lot of exciting possibilities for research and development.
Absolutely. So for all of you listening, AI researchers, engineers, developers grappling with these tools, maybe think about which of these challenges hits closest to home for you. What's the biggest bottleneck you see in using AI for software tasks day to day?
Yeah, and perhaps even consider if there are small experiments you could run in your own work, maybe inspired by some of these paths forward.
Definitely encourage everyone to check out the paper itself for the full details and all the references. It's a really valuable contribution. Thanks for joining us for this exploration of AI for software engineering.